use this for this simple distribution, but for complicated distributions, it'd be really common for me to do like what's called Newton's method, and basically doing this, but automating it. You know, I could look at every value pretty quickly between 40 and 50 and find the best one. You know, I could look at it 1,000 values between 40 and 50 and estimate it to the nearest tenth of a unit. Or if it's more complicated, I could do some elaborate scheme to, you know, jump here, then in the middle, and that's what Newton's method does. It finds 2 points, and then it finds the middle, and finds the slope of that, and iteratively breaks the problem down to do hill climbing. Okay. So that's a reasonable way of scoring how good this is. But this, I can't use this to find my variability. This doesn't help me estimate the variability. But I could, here's a little way of doing that. I could look at I could basically do a histogram of the variability of one function of the data and a histogram of the variability of my model and compare the two visually. Okay, so that's what the next version of this function does. And so the first part is going to be essentially the same, and without going into too much detail, I'm going to make 2 panels and look at the cumulative density, estimate the cumulative density of my data and of my estimated data. So here, let me go back to, I think 45 was about the best. So here's my new one, plot mean 3, and you know, I had a mean square error of 1100, but if I have a variance of 2, my cumulative distribution is going to, for the model is going to be really like a step function. You know, that's what's going to be right here. It makes sense. Nothing, 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 everything. And you know, so if I go from negative to positive, it's all centered in the middle. And it turns out that the variability here is what I'm going to be using to make most of my inferences, how variable the data is, and I have it completely misspecified here. But now I could take this and maybe I could go 10. Now that's getting better, but mine is still steeper. And you know, I can eyeball that. 40, that's still steeper. 48, 30 is pretty good. 48, 35. So eyeballing this, you know, these are pretty good. I could come up with a measure of how good this is as well. Maybe my 45 is going to be up a little more. You know, that looks pretty good. So this is a pretty decent way of doing it, that I can say, here's my true distribution, and here is my model, and through just hand adjusting things, I could judge how good, I could come up with parameters that fit the distribution. Now there are times when you have to do this, and the times that are serious when you have to do this, they've come with all types of methods that will do it for you. So it's pretty rare for normal statistical analysis that you have to do this type of thing, because we have something called statistics. And it turns out that for a given distribution, for any given distribution, or for many given distributions, especially ones in the exponential family, of which the normal distribution is one of them, you can always find a statistic of data that can estimate these parameters. And it shouldn't surprise you to find out that if I compute the mean of my data, that will estimate the best parameter for the distribution describing it. So the mean is a statistic on the data, and that's what I can, instead of doing this by hand and adjusting it, I can take a statistic of the data and compute a function on it to estimate it. And for many simple distributions, there are simple ways of estimating based on functions of the data. But it depends on the function of the data and what my cost function is. What is it that I want to optimize? So if I want to optimize squared error loss, then it's well worked out what my estimate of how to compute the mean and how to estimate the standard deviation to get exact answers to this. But there are other things I can estimate. There are other functions, and another really common one is to maximize the likelihood. And so maximum likelihood estimates are often different than an estimate like this. A maximum likelihood estimate uses different logic. It doesn't minimize that cost squared error loss. It maximizes the likelihood. So what you do is you say, if you imagine that distribution function that has that density that we interpret as a likelihood, there's sort of a ridge here that flattens out and goes up and then flattens back down. And so every value lives in that normal distribution somewhere and is associated with a height of the density function. And I might, instead of picking the value that minimizes squared error loss, I could pick values that maximize likelihood. And so those estimates might be different. The mean, in this case, the mean won't be any different, but my estimate of the standard deviation might be. So if I want to maximize likelihood, my estimate of the standard deviation might actually be different than if I were minimizing squared error loss.
You can't do both at the same time.
Well, you get different numbers.
Right, but if you did them both, like the whatever number minimizes error loss and maximizes likelihood with both of those as being controls.
No, I mean, those are typically either identical or in conflict. I mean, it's like saying, I want the car that drives fastest and I want the car that is cheapest. You can't have both.
But you can have the fastest, cheapest car. The fastest of the cheapest cars. Right?
But that's not either the fastest or the cheapest.
But it's like the cheapest of the fastest, or it's the fastest of the cheapest.
Well,
Is that what you're saying?
There are different, there are reasons to use a likelihood instead of a loss function. And it has to do with interpretation, and it has to do with often using Bayesian methods. So if you use a likelihood, one thing you can do is pick the most likely parameter value. But another thing people do is, instead of saying, if you're working with likelihood, you say, well, for a given parameter value, this is the most likely parameter value given my data. But I could also say, this parameter value here is pretty likely too. It could have very easily have generated my data. This parameter value here, while not, it's also pretty likely. And so a modern approach people use is, instead of just looking at the maximum likelihood, they look at the distribution of possibilities. And this is an approach known as a Bayesian approach, where you say, well, there's a lot of parameter values consistent with my data. And so I'm not going to assume that it's one of them. I'm going to assume, all I'm going to assume is I have confidence about a distribution of possible parameter values. And so, these are many different approaches to this problem. And in each case, you do it by defining what you mean by good. And here we've defined a couple different meanings of good: squared error loss or likelihood. And then find a way of finding a good estimate based on that. And maybe it's a single estimate, or it's a range of estimates, or it's a distribution of estimates. So that's what parameter estimation is. Now, so it turns out that the best estimate for the normal is going to be the mean. So let's see what the mean of x2 is.
Professor, if you don't look at the spread, why do we actually, see the spread of the gray ones are our data, right? I mean,
The black ones are data.
the gray ones are.
The gray ones are simulated data from my hypothetical distribution. That's just to help us visualize, do we have the right distribution?
So it has to be, so we don't sort of coincide it with the data, or should it all be closer to the line? Visually, which one do we go for actually?
If you want to estimate the mean of the distribution, if you can just ignore the gray stuff for the moment. All I'm doing is trying to find the best line that describes the mean of my values, the middle of my values, and the way to do that is actually to compute them. The best way to do that,
By the square error.
according to the squared error loss, is to find the mean of my data. And the mean turns out to be 44.7, and I thought it was 45, which is pretty close, right? So if we do plot mean 3, x2, and then I say 44.72, and the